So now what we'll look at is what is called a sorting algorithm. So you might have come across this term called sorting already, but so what we are going to look at is, say, given an array, which could be also like considered as a list of integers. That's what you will do for an exam question. So given a list of integers, so what you're going to look at is an array-based algorithm, and you will extend that for a list. Okay. So given in this case an array of integers, you want to sort them such that after you go through the sorting algorithm, you have a sorted list of that array integers. Okay. So different sorting algorithms you are going to see in this course as well as in the next course 323. Okay, and as we go through the sorting algorithms, we'll also analyze the time complexity, and eventually you should be able to compare the time complexity versus space complexity of these algorithms. Okay, let us see a very basic and a classical algorithm called selection sort algorithm. So all these sorting algorithms typically go through iterations, and in each iteration some element gets moved or shifted to all the way to its final position in the sorted array. Okay. So in this case you will see as we go through this algorithm how the elements get shifted and move to their final position. So we are going to consider an array implementation. So the index of the array goes from 0 to n minus 1. So when I say orderable elements, that means you can compare two elements, two integers, and say which one is greater among two integers, and then accordingly you can decide. So that's what orderable means. So when you compare two elements, you should be able to decide which one is greater and other one is smaller. Okay. So you're going through iterations. So you're going to have n minus 1 iterations, and we'll use the loop index itself to keep track of the iteration. So this index I is also the iteration number, and we'll start that from 0 to n minus 2. So together totally we are going to have n minus 1 iterations. Now I'm going to use a variable, temporary variable. It's called MinIndex, and it will represent the index where the minimum element is from index I to n minus 1. So you start from index I to be 0, and for that iteration MinIndex initially set to I itself, which is 0, will eventually take up the value where the minimum element is from index I to n minus 1. So that means, like in this code, in this example, the first iteration 0, I equals 0, MinIndex is also initially 0, because that's how we are setting MinIndex equals I. But eventually MinIndex will take up the value 7, because that's where, starting from this index I equals 0 all the way to n minus 1, the end of the array, the minimum element is. So the minimum element is 1. Starting from index 0 to all the way to n minus 1, the minimum element is 1, and that's at index 7. So you are at index I is 0, and MinIndex will eventually take the value 7, and what you'll end up doing is swapping those values. So 1, that's the minimum element, gets swapped with this index element at index I, which is 5. So 1 will come here and 5 will go there. So basically you can see that element 1 has shifted to its final position. In the final sorted array, 1 has to be here at index 0, and that's where 1 has moved to. Okay, so that's what happens in iteration 0, which is the first iteration. Then the second, we do the same thing repeatedly in the subsequent iterations. So in iteration 1, I will be 1, that's your iteration index, and MinIndex will also be initially 1. So that's why I've colored that, say, yellow, like 6. So the element value is 6, but MinIndex is the index, so that's initially 1. So what we are going to do in this iteration is, starting from index I, which is 1, all the way to n minus 1, we are going to find what is the minimum element. And in this case it happens to be 3 at index 4. So MinIndex will take up the value 4. And then we're going to swap the value at MinIndex, which is 3, with the value at index I, the iteration index, which is 6. So 3 comes here, 6 goes here. So you can see now the second smallest element, which is 3 in this array, has moved to its final position. So in the first iteration, the first smallest element, you can call like that, has moved to its final position. The second iteration, the second smallest element has moved to its final position. So in the third iteration, which is iteration 2, so the iteration index will be 2, and that will also be the initial value of min index. You're going to find what is the minimum element starting from index I to n minus 1, and what is that corresponding index. So in this case, the minimum element starting from index 4 all the way to the end is 4. So the corresponding min index is 3. So all you have to do is swap the value at min index, which is 4, with the value at index I, that is 5. So swap 4 and 5. So 4 comes here. So that's 4 is the third smallest element, and that has moved to its final position in the last iteration, in the third iteration. Now in the fourth iteration, you can see which is iteration 3. So index I is 3. Min index is also 3 to begin with. So you're going to find, starting from this index, what's the smallest element. So the data currently you have is 5 at this min index. So you have to find something that is less than this 5. See, that's what we have been doing at each iteration. So currently, say in the first iteration, you have min index as 0 and the corresponding data as 5. So you want to be able to find something that is less than 5. And as you keep finding something that is less than 5, you will keep updating the min index. That's the detail of that iteration. Okay, so you can see now the details of a particular iteration, and then look at the pseudo code. So you start with min index is, say in this iteration is 0, I equals 0, and the corresponding data is 5. So now what you will do is you will run through an inner loop, which is, say, index j equals I plus 1 to n minus 1. So you are at iteration index I. So run this inner loop from j equals I plus 1 to n minus 1 and traverse through the elements from I plus 1 to n minus 1. So that is through index j. So if anything at index j is less than what you think is the current minimum value, so how you can check? A of min index. So min index is initially 0 here in this first iteration, and the corresponding data is 5. So j is 1, the data is 6. So you are checking, is 6 less than 5? No. So just keep the min index at 0. Then you come to index j equals 2, check the data at index 2, 5 is less than 5? No. Then j equals 3, now you check 4. Is 4 less than 5? Yes. So min index will be then updated to 4, that is the j index. Then continue. So j is 4, the data currently there is 3. Is 3 now less than what your minimum data is, which is 4? And it is true. So that means you can, a of j is 3 less than the data currently at min index, which is min index is now 3 and the data is 4. So you update min index to be this index 4. So the minimum element is currently the data value is 3. So now move the j index. So you have 10. Is 10 less than 3? No. So keep moving. 9 less than 3? No. Now 1 less than 3. So min index is now set to 7. So now move the j further. Is 7 less than 1? No. 8 less than 1? No. So after you reach the end of the array, you have found where the minimum element is. That's the min index. So when you come out of this inner loop, which is the j loop, that is like after you go through the entire array, you swap the value at a of I. So I is still at index 0. That's where you're starting, with the value at min index. So the min index is 7. So you swap the data at the two index values. So 1 comes here, 5 goes here, and that's what you repeatedly do in each iteration. So let us do one more iteration. Iteration index I equals 1. So min index is also 1 and the data is 6. So run the j loop from I plus 1, which is 2 to n minus 1. So I is 1 means I plus 1 is 2. So j will start at 2. So the data there is 5. Is 5 less than 6? Yes. So min index will be set to 2 now. You go inside this if block and set min index is 2, but I is still 1. I is not changing in a particular iteration. That's why it's called iteration index. So it is still 1, but min index is 2. Then move the j loop. J is 3. Now you see 4, which is less than what you think as a current minimum, which is 5. So update for 3 to be the min index. Then move the j further down. You see again 3 less than 4. So update min index to be 4. And then you see 10 not less than 3. Then 9 not less than 3. So anything further down is not less than 3. So min index will be 4 starting from this index I equals 1 to n minus 1. So that means when you come out of this inner loop, you swap a of I with a of min index. So a of I is 6, that's the data at index I, is 1. So swap the data at index I equals 1 with the data at min index, which is 4. So swap 3 and 6. So 3 comes here, 6 goes here. So as you do this in say iteration index 3, that means I equals 3 and min index is also 3 to begin with. The data there is 5. So you will be running the j loop starting from I plus 1 to n minus 1, and the data you see at j equals 4 is 6, not less than 5. So keep moving the j loop. Min index stays at 3. Then 10 not less than 5. Now you see 5, which is not less than 5. So min index still stays at 3. And then 7 and 8. So none of the data to the right of this I is less than the data there at index I. So when you come out of the loop, min index will be still at I. Min index is also I. So you will be swapping the data at index I with the data at index I. So it's still okay. You are swapping the data here to itself. So 5 is now considered to have reached its final position. So the 5 you have here is this 5 that you had before, not this 5, because the way the pseudocode is set up, the data further down has to be less than, not less than or equal to. So it has to be less than. So you are not unnecessarily moving the data around. So you keep, if you have 5 and the smallest you can see further down is also 5, just keep this 5 as it is here. That's the smallest. So now in the next iteration, as we continue, I is 4, min index is also 4 to begin with, and then the j loop will run from I plus 1 to n minus 1. So j is 5. So the min index is 4, the data is 6. So 10 compared with 6. 10 is not less than 6. 9 is not less than 6. But 5 is less than 6. So min index will be now moved to set to 7. Then compare 7 with 5, 8 with 5, nothing is less than 5. So min index will be min index will be 7, that's where the minimum element is. The iteration index I is 4. So you swap the data at the 2 index values. So 5 comes here, 6 goes here. And you keep doing this for all the way to iteration 8, which is n minus 2. So you have 10 elements. So the loop, the iteration index loop runs from 0 to n minus 2. So the end you will have a sorted array. Okay. So as you can see in the last iteration, which is iteration index 8, min index will also be 8. And then so the j loop will just run from I plus 1 to n minus 1, which is just this in j will be 9. So you're comparing the data at that index j to the data at min index, which is 8. So 10 is not less than 9. So you simply come out of the for loop, the inner j loop, and you will be just swapping 9 with 9. Okay. So the data at min index is 8 and the data at index I is also 8, and you swap with itself like we did earlier with the 5 with 5. So you can see you can stop your iterations here. You don't have to really move the iteration index to the last index, because you see the inner loop runs from I plus 1. So if you move your I to n minus 1, j will become I plus 1 means n. There's no really index n, right? So when you have only one element and that's the last element, it's already in its final sorted position. So that's why we run only n minus 1 iterations. even though you have n elements, you run only n minus 1 iterations, starting from iteration index I equals 0 to iteration index I equals n minus 2. That's totally n minus 1 iterations. Okay. So any question on the logic of selection sort? So an array-based implementation is straightforward. Just you have to use the pseudo code almost as a template and write the C++ code. You can still use this as a template and extend it for a list. So that's what we will be doing it for your exam question. So if you want to use this with a list, the main thing is finding where the minimum element is starting from a current node, right? So think about all these things as node. I think I have a figure here. So think about, this is the current list you have. Okay, so this is, say, the list you currently have with all, say, r random integers, and you know how to set up such a list. You have seen the code for that. So this is, say, your current node pointer corresponds to the iteration index I. Okay, so you want to keep this as a reference, and starting from this node, now we want to check the data. Which node has the smallest data starting from this node? And if you look at this figure here, this node at address 900 has the minimum data. So what you want to do is basically be able to find where, starting from this node, the current node, what node has the minimum data. That means you need to know where that node is. So the address of the node with the minimum data is 900, and that's the address you need to know. That's like the min index there. Okay, so the min index is also like an address, right? So here you need to really know where that node is with the minimum data. So you have to use a pointer to store that address with the minimum data, and then swap that node's data with the current node's data. So you have a pointer pointing to the current node, and you will have a pointer that stores the address of the node with the minimum data starting from that current node, which is in this case 3. So swap 3 with 10, 3 comes here, 10 goes here. Okay, and then what will happen? You move your current node pointer to the next data node, which is the node at address 70, the data is 25. So starting from this node, you have to find out what is the node with the minimum data. So if you visualize things, so the 10 has moved here. So it will be 25, 10, 7, 9. So the minimum data now is the 7 at address 500. So you store that address in a pointer and swap that node's data with the node currently pointed by current node pointer. So current node pointer now has the data 25, that's current node's data. So you swap the data of that current node with the data pointed by that pointer that stores the address of the node of the minimum data, which is 7. So 7 comes here, 25 comes here. So now you see the list will have 3 followed by 7 followed by the 10 you have here, and then 25 and 9. So 10, 25, 9. So now 10 swapped with 9. So 9 comes here, 10 goes here. Then 7, it's already the minimum. So it will be the last, also the last iteration. Okay. So you can use a similar logic that we went through for the array and extend to a linked list. So to help you out to do this question, what we are going to look at is the code. That's the most important part of this implementation, and that's what I'm providing you. Okay, and then you have to write the loop that we just that I just explained to go through the iterations. So what we're going to look at is the code for, in one particular iteration, you're going to find what is the minimum element. Okay, what's the address of the minimum, the node with the minimum data. So that's what I'm calling this, find minimum data node address. So this function is going to give you Now this code is not really implementing selection sort. So what this code is doing is it takes up a list object. So on the entire list, it's going to find out what's the address of the node with the minimum data. So once you know how to do this, you can modify and extend this logic to implement the selection sort algorithm. Okay, so that's how you kind of make use of a logic and work around it and extend and modify your code. Okay, so let us look at it. Any question on the logic so far on selection sort? Okay, so this is code number 7 in the zip file, so you can open it and look at it. So let me show that so that you can understand the entire context of the code. So I may not have it here. Let me open it. Alright, so the context here is, again, I am getting the list size from the user, setting up the values. So use the insert at index function to set the values. So this is what this main function is doing. So once you have built the list, all it tries to find is call this function that we are going to go through and pass the list object as the argument and find the address of the node with the minimum data in the entire list. Okay, the entire list, it's going to find the address of the node with the minimum data. So that's equivalent to finding the index where the minimum element is in an array. Okay. So once you get that address of the node with the minimum data, if it is not null, that means it will be usually null if the list is empty. If it is not null, means the list is going to have some element and you have the address of the node with the minimum element. So then if it's not null, you can call the get data function on that pointer, because it's a pointer to a node object. Okay, so you can use the get data function and print the data. That's the minimum data in the entire list. So and once you look at this function code, you can use a similar logic to implement the selection sort algorithm. Okay, so let's look at this code for finding the address of the node with the minimum data. And we'll use this example and this code here. Alright, so let us say you currently have this as the list, and the objective here is find the address of the node with the minimum data in the entire list. So we again use a similar logic in the last class also. You see here I'm calling this find minimum data node address from the main function, and this is a member function in the list class, this find minimum data node address. Let me take it back. Okay, so this is not a member function in the list class, this is a function outside the list class. So this is my class list. So if I do this, so all the functions, the list class you have seen. So this is another way you can make use of the member functions in list class. So this is a function that is written outside the list class, like the main function. The main function is also a function outside the list class, right? So this is a function that is written outside the list class. But still you should be able to access the list. So how can we do that? So I pass the list as the argument. Okay, so the integer list that you created in the main function is passed here. So the object name is passed here. So since this is a member, this is not a member function, this is a function outside the list class, we cannot access the head node right away, because only inside the list class you have the head pointer, and any member function inside the list class can access the head pointer right away. But since this function is outside the list class, the first thing we have to do is, we have done this similar thing last time, is to get the head pointer. That's the key thing, that's the only member variable in the list class using which you can access the head node and through which you can move further down. So how to get that head pointer value? You use the list object that you got as the argument. So that's the list object. So you have to use a dot operator and call the get head pointer member function on this list object. So get head pointer is a member function in the list class. So you call that member function on the list object and that will return the head pointer value. So now you have the address of the head node. Okay. So using the address of the head node you can access the list. So this logic is very important to understand. So you are calling this, so this member function first of all is written outside the list class and you are passing to this function the list object from the main function. So this function outside the list class needs to first get a handle on the list. How to get a handle on the list? Call the get head pointer function on the list object and that will return the head pointer that stores the address of the head node. Using that you can access the list now. Right? Any question on this logic so far? Alright, so let us see now the code for this. So the head pointer stores the address of the head node in the list. And then you can get the address of the next data node by calling get next node pointer on the head pointer. So the current node pointer is going to store that address, let's say 200, the head pointer is say 100, and so what we need to check. Alright, so now as I said, we need to find the node with the minimum data. That's the objective of this function. So let us use a temporary pointer variable called min data node pointer. That's also of a point of the node class. So you say node star min data node pointer, and I have not initialized it right away at the time I am declaring it. So I am just declaring that pointer to be of type node. So I will initialize it using this if in the following code. So if the current node pointer is not null, that means when will be current node pointer not null? Something like this, when the list has at least one data node. If the list has no data node, it will be like the next node pointer, the head node will be 0, null. So that's the case when the list is null, and with this statement that you have head pointer arrow get next node pointer, current node pointer will be null right away. So that means the list is empty. So if current node pointer is null, that means the list is empty. Return 0 as the return value because you have returned the address of the node with the minimum data and the list itself is empty, so you return null as the return value 0. So that's why in the main function you check the return value of this find minimum data node address function, and if the return value is 0, okay, then you cannot call the get data function on the minimum data node pointer. So that's why I code else block and just print list is empty. So you can print the data only if the pointer value returned by this function is not null, and that will be not null if the list is not empty. So if the list is not empty, that means you at least have one data node in the list. That's when current node pointer will be not null. So you get inside the if block and assign the value of current node pointer itself to min data node pointer. So that's like, in your you have done this code in 119. So if you want to find the minimum element in an array, assign the first element itself to be the minimum element as a temporary minimum element, and then go to the rest of the array. And we have seen this code also, a pseudocode for this in the first module, and that's a similar logic we are doing here. So here we have to keep track using the addresses, using the pointers. There in an array use the index or the value itself at that index. So here we'll use the pointer. Okay. So min data node pointer will initially be the address of the first data node, and the address of the first data node is stored in current node pointer. So if current node pointer is not null, min data node pointer takes up the value of current node pointer. So min data node pointer will also be this 200. The current node pointer is also 200, and that's the kind of initial setup. And since now you have a handle to the first data node, you can move the current node pointer to the next data node. So that's what I do inside this if block itself. So once I assign the value of current node pointer to min data node pointer, I move current node pointer further down to the next to store the address of the next data node. So you can get that using this get next node pointer function. Call that on the current node pointer. That will return the value 70, the address of the next data node. So that will be the new value of current node pointer. So it will be 70 and pointing to the next data node. So that's what you accomplish in this if statement, if block here. Okay. So when you come out of the if block, you have to see if you can traverse further down. You can traverse further down only if current node pointer is not null. So if current node pointer is null at this stage and you cannot get inside the while loop, that means the list just has one element in it, and that one element itself is the minimum element, and min data node pointer will be storing the address of that element, because that's what you accomplish by making the min data node pointer to take up the address of the first data node. Okay, and so everything will still be okay. So if current node pointer is not null, you cannot even get inside the while loop. You just simply come out of it and say return min data node pointer. That means you're returning the address of the node that has a minimum data. So if you have just one element, one data node in the list, that itself is a minimum, and min data node pointer will be storing that address of that node, and that's what it will be returning from the main function to the main function. If current node pointer is not null, like in this case it is 70, then that means there's more than one data node in the list, and you have to really find the minimum among all the data nodes out there. So that's the code that we are going to look at now in the while loop. So if current node pointer is not null, get inside the while loop, and now it's the business of comparing the data pointed by current node pointer with the data pointed by the min data node pointer. So min data node pointer is storing the address of this node at address 200. So the data is 10. So compare that data with the data pointed to the node at the pointed by the current node pointer. So that is 25. So min node. So this node's data is 10 compared with 25. That's what you're seeing here. Min data node pointer arrowgate data, which is 10, compared with the data pointed to the data at the node pointed by the current node pointer, which is 25. If 10 greater than 25, no. So we don't go into the if block, just move the current node pointer further down. So current node pointer takes up the address of the next data node, which is 900. Sorry, I have a typo here, so this should be 900. And now compare the data at min node, and now check again if current node pointer is null. It's not null, it's 900. So compare the data at the min data node pointer with the data pointed at the node pointed by current node pointer. So it's 10 compared with the data out there, which is 3. Is 10 greater than 3? Yes. So what we need to do is make this min data node pointer now to store the address of this node. Okay, and we have a handle to this node using current node pointer. So you can simply say if the data at that pointed, if the data at the node pointed by the min data node pointer is greater than the data at the node pointed by the current node pointer, like in this case 10 greater than 3, then min data node pointer can be now set to be the value of current node pointer. So min data node pointer takes up the value 900. And then you come out of the if block and move the current node pointer further down. So current node pointer will now take up the value of the address of the next data node, which is 500. And then continue the loop. Check if the current node pointer is null or not. 500, so it's not null. So get inside the loop and now compare the data at the node pointer by min data node pointer, which is 3, with the data at the current node, which is 7. So 3 compared with 3 greater than 7. No, it's not true. So don't go into the if block. So min data node pointer still stays at 900. then move the current node pointer further down. So current node pointer will be 700 pointing to this data node. Not null. So compare the data at this node pointed by the min data node pointer, which is the data is 3, compared with data currently pointed by the current node pointer is 9. So 3 greater than 9 is not true. So don't go into the if block and just advance the current node pointer further down. There's no next data node, so next node address is 0. So current node pointer will take up the value 0 now. Now current node pointer is 0, so don't get inside the while loop, come out of the while loop and return the value of min data node pointer. So by the time current node pointer becomes null, that means you have traversed through the entire list, you have found the address of the node with the minimum data, which is 900. So you can access this node outside this function. So you see here the logic is we return from this function the find minimum data node address, the address of the node with the minimum data in that list, and you can access that address in the main function. So in the main function, once you get the address as a return value, you can say that whatever the, so you can give a different name for this pointer because this is in the main function and this is a different function. So that's why I made a difference by putting a capital M for the min instead of the lowercase m. So min data node pointer arrow get data will print for you the address at the data at that node that has a minimum data. Okay. So this min data node pointer, the main function, will take up the value of this 900 that you're returning, and using that address you can refer to that node at that address and print its data, and that's what I'm doing here. Right? Any question? So this is something important to understand, and that will be useful for you to implement the selection sort algorithm. So let me save this